minus j omega n, where omega is the real frequency variable and n denotes the time variable. So that means that given a signal, it represents or breaks the signal in terms of these complex exponential signals. So when Fourier transform as such could be applied to continuous signals as well as discrete time signals. Discrete time signals, we mean that time is sampled at uniform intervals. So when Fourier transform is applied to discrete signal, it is referred to as discrete Fourier transform. So these are the equations which you can find in any standard textbook, which gives you, this is the equation which gives you the Fourier transform. So x of n is a time domain signal, and then x of k is the frequency representation of the signal. So you can also define an inverse Fourier transform where you plug in this frequency signal into this equation, and then you would get back your time domain signal here. So you would often hear about FFT, how it is related to DFT. Let's look at here. Fast Fourier transform is a fast algorithm or fast implementation of discrete Fourier transform. Typically, if you have a n-point signal or n-point sequence, the DFT would take about n square complex multiplications, and if you implement using FFT, fast Fourier transform, then that would take about log n steps or n log n computations. So I don't want to further go into details how this reduction in the computation takes place. You should be able to get this information, or should be able to know this by a more regular signal processing course or by the textbook which is there in the website. So now let's look at the relation between speech and the FFT. So here we are seeing a speech signal here, and then what we are showing here is the FFT or spectrum of the speech signal. So importantly, what I want you to observe here is that you should be able to see there are some peaks here in the spectrum. So keep in mind that these peaks convey dominant frequency components present in the speech signal. So the peaks, which are referred to as formants in a speech spectrum, are dominant frequency components in the signal. So they provide useful information for speech recognition. That means the identity of a sound could be known from the formant locations or formant positions. That means where there is a peak, and by the location of these peaks you should be able, the sounds are distinguished in the speech recognition. So what we mean here is each sound has its own distinctive formants. I am just showing an example of two sounds E here. One is E, as in bit, has formants at 400 Hz, 1900 and 2550, and formant A, as in bat, the sound A, as in bat, has formants at 690, 1660, 2490 Hz. So if you know, if you look at the spectrum and then you observe the peaks at these locations, then you know that this is an A, as in bat. Otherwise, if you observe peaks at these locations, 400, 1900 and 2550, then you would know that it is sound E, as in bit. So the formants carry important identity of the sound. So that's a very important point to recognize. So that's where the spectrum is essential or plays a major role in building speech recognition systems. So let's look at how we compute FFT over the entire speech signal. Again, as we have seen in the previous lecture, that we would divide the speech signal into shorter regions. That means we would use shorter analysis window, and on each analysis window we would take the signal here and then apply FFT and get the spectrum. Then we would proceed to next analysis window, take the signal, apply FFT and then get the spectrum. So similarly we'll proceed for all the analysis window until we reach the end of the, or like until we reach the last analysis window. So as a summary here, speech is analyzed over short analysis window, and for each short analysis window a spectrum is obtained using FFT. So thus speech is represented as a sequence of spectral vectors. So you should listen to further lectures for some more post-processing that takes place with these spectral vectors. But as of this lecture, please understand that speech is represented as a sequence of spectral vectors, and it is these spectral vectors which are given to pattern classifiers like neural networks, hidden Markov models for speech recognition purpose. It is this slide I think is important to summarize the feature extraction. The first step is speech is analyzed over short analysis windows, and for each short analysis window a spectrum is obtained using fast Fourier transform, and this gives you a sequence of spectral vectors to represent a speech signal, and these spectral vectors are given as input to machine learning models for speech recognition purpose. So you should be able to find more additional reading in this chapter. We'll continue with the next lectures with further more information about spectral features. Thank you.